All right. So we're basically going to be doing the implicit differentiation of this per time. Okay. So what that means is, and you don't have to write this part. I'm just going to write it for a second. If I asked you to take the derivative of y cubed in terms of x, what would you do? What would be the derivative of y cubed?
Y squared.
Good, times what? dy dx. So you just took the derivative in terms of x, correct? That means that as dy changes for x, okay? What you're going to be doing today is you're going to be taking every derivative in terms of time. Because we're going to be talking about related rates, okay? Related rates are how things change over time, okay? So how the area changes over time, how the radius changes over time. So everything is over time, okay? Literally over time. dt is going to always be the bottom. So that kind of helps you remember what's happening. All right, so we're going to basically differentiate this formula as time being our variable, t. So what would be the derivative of a? 1.
A prime.
Just a, yeah. So or just 1. So it would be 1 times dA over dt, right? Just like implicit differentiation. You guys remember that. You guys did pretty good with that. Pi. Is pi ever going to change? Is that a variable? No, it's a constant. Okay. It is going to be 2 pi because the derivative of r squared is 2r. So it's going to be 2 pi r times what?
dr
dt. So let me talk a little bit about what we just did. This is the change in area as time goes on. Okay? The change in the radius as time goes on. Okay? So we use these formulas to talk about when these scenarios occur. Now, can anybody tell me what this formula does? The original one.
Area equals pi square, pi r squared.
Which is area of a
circle.
Good. So this formula finds area of a circle. This formula finds the rate of change of area of a circle. Okay? Change in area of a circle. So if a circle's area changes, what else is going to inherently change?
It's
volume.
Yeah, it's circumference. That's true. Which is reliant on what?
Its radius.
Its radius. So if a circle's area changes, its radius changes. If its radius changes, its area changes. They're simultaneous, right? That's just inherent for a circle, correct? So let's think of a scenario when this could happen, okay? Now keep in mind, these are models, okay? I know a lot of things in life aren't perfect circles, but we use them as models, okay? What's up?
If a cookie, like when you bake it, it gets larger.
That's a good one. Perfect, yeah. So exactly. So if we have a cookie unbaked,
Good job, Ryan.
okay. All right, and then as you bake it, it's going to expand into a bigger cookie. So not only does the area of the cookie change, but also it's what?
Circumference.
Its circumference and its
Radius.
the radius. So they both have our rate of change. That means that these two variables, somebody call them variables because they're rates of change. So the rate of change of the radius, the rate of change of the area, that's what we would use it to find.
I'm
Okay.
culinary 4, so I know all this.
Ah, perfect. Yeah, perfect for this class. Yeah. All right. So this one here, we were talking about this earlier. It's what? What of a circle?
Circumference.
Yeah, this is circumference of a circle. So this one's going to have kind of the same applications, but instead of finding the area of the cookie, it's instead going to find the,
Circumference.
which is basically the perimeter of the
Yeah.
cookie. Okay. So what would be the derivative of this?
1 equals
Or 1 times?
1 times dt or dc over dt.
2 pi times
dr over dt.
Good. So you see how both of the variables went away because we took the derivative and they were only for the first power. Okay, that's implicit differentiation in terms of time. Okay. So Brandon's example still applies here. If we have a cookie, before it's in the oven, it's tiny. So its circumference is little, and then as it bakes, it gets bigger. Now, like I said, I know that things are not perfect circles, so these are models. Okay, we use things to model things that are similar to their shape. Because obviously that would be a much more complicated formula. So any questions about that?
Where are we gonna go with this?
We're gonna be doing word problems where these things happen. We're gonna have to find the derivative and all that stuff. So that's what we're doing tomorrow. But I'm stepping you into it slowly so that it's not overwhelming. Okay, that's the main idea here. All right, next slide. It's not too bad, I promise. We're gonna go through it slowly enough that it
Is
won't
it
be
better than the
scary.
graphing stuff?
I like it better.
Okay.
Yeah. Okay. So what is this formula? Everybody here knows what that is. Pythagorean theorem. Our old friend.
Can we go back to doing that instead?
Well, we
That's a
kind
good
of are
point.
in a calculus way. So Pythagorean theorem. What is its purpose?
Find the sides of this triangle.
If you know two sides, it helps you find one of the other sides, correct? But it only works for certain types of triangles.
Right triangle.
Right triangles, correct.
It could
So-
be used for architecture.
It is used for architecture for sure. But keep in mind, we're thinking of things as they change, so we have to think more specific. But before we do that, let's go ahead and take the derivative of this thing. Let's.
I was just thinking you bake a piece of pizza. That was my first thought. It does not get bigger.
No, not really. So what would be the derivative of this?
Isn't it like
2
2a
and then
dA dt
uh-huh plus
plus 2b
uh-huh
dB over dt
Yep.
equals 2c
mhm
dc over dt.
yeah.
That's hideous.
good job, Jake.
Now here's the good news about this. Anybody who is big brained and been doing this kind of math for a while, okay, they see that we can factor something out on the left.
2.
A 2. So if we take out a 2, we end up with this. And remember, anything d is a rate. Okay, we end up with using rates. We're gonna plug stuff into that and all that. We'll get to that tomorrow. So we end up with this. Okay. Now, if I divide both sides by 2, what happens with the 2's?
God. No more.
They cancel out. So you're going to see in problems, people already know when they have to take the derivative of Pythagorean theorem, they know the 2's are going to cancel. Now, you didn't have to know that. You could still do it with the 2's, but it's just like a way to speed the process up. You don't have to worry about multiplying everything by 2 because it's all the same. So I have a little graphic to show you guys real quick. Where is my eCampus? That's not eCampus. It is, yeah. Good catch. All right, let's see. The portal.
Wait, so what is the application of this one?
I'm going to show you right now a little graphic of it. I thought I had it open, but apparently it wasn't, so I'm getting there.
Cool.
All right. This one. Scroll for me. There we go. Okay. So related rates prequel. The cool thing is on here I put little examples of things that are little, drawings and whatnot. So think of this red as a house, okay? Think of this gray line as a ladder. So what you're going to notice is if the ladder slides out on the house right here, see what happens? The ladder never changes length. Yeah, the ladder never changes length, no matter what. The hypotenuse stays the same, but what changes?
The angle.
The angle does change, and we'll talk about that in another problem, but you're right. So essentially the A and the B change, right? But the ladder stays the same. So this would be an example of a change in the lengths, okay? Where a ladder falling down the side of a house would be one of those examples, okay?
So what's like with all due respect, useful one?
That is one that's useful. Like
I mean,
something...
If my dad's on the ladder and starts falling, like, oh, do you calculate like the distance he has left?
Well, no, but it's more like things that we would use in like architecture for safety purposes, like maybe like building a ladder. Like how strong can I make this angle and how tall for it to be stable type of thing.
Okay.
It can get more in depth. We're keeping it real simple today, thinking basic.
Okay.
But it can get more elaborate. So yeah, a ladder sliding out from a house. So if you have a house right here and you have a ladder. Now the cool thing about this one in particular and why we'll use this example a lot is because the hypotenuse never changes. So we're going to talk about that as well. It's not a rate of change, so you can actually plug it in before you take the derivative, and we'll get into all that, but that's the main idea for that one. So the next one. Anybody know what this formula is for?
Volume of a circle.
Cylinder.
Volume of a cylinder. Okay. That's volume of a cylinder.
It's a good cylinder.
Thank you. So, with the volume of a cylinder, we have a radius and we have a height, correct? Now, something that we'll get into is this has two variables in it, which can get tricky. But the good news is, in a problem, they're always going to give you some ratio that they compare. So, like, as the height grows, the radius is going to grow proportionally. Okay, so we can use that information to help us with a problem. But today, we're going to treat it as two separate variables because we don't know they have that proportion. So, what you're going to notice here is we have the product of two variables. What does that call for in calculus?
Product rule.
The product rule.
Need it.
So, we're going to start by taking the derivative of volume, which is going to be
1 times dv over dt.
good, 1 times dv over dt. So that's volume changing in respect to time. And then what I'm actually going to do is I'm going to put the pi outside. Okay, because it's a constant, it's not going to affect anything. That's going to make my product rule easier. Okay. Now I'm going to do the product rule. This is essentially my f of x, and this is going to be like my g of x. So the product rule says I'm going to take the derivative of f of x and multiply it by g of x. So what would be the derivative of r squared?
2r.
Times
Times dr dt.
dr dt, and then times g of x, which is h, plus, hopefully I have enough room here. What's the derivative of h?
dh over dt.
Yeah, 1 times dh over dt times r squared, the other thing. That's just the product rule. So yeah, you're going to do one with that. So volume of a cylinder. There's a lot of different examples you could think of where this could change. Any ideas? Yeah.
So when a soup can, like it gets like a hole in it, and
Okay.
like, the stuff inside gets exposed to the elements, it may like get bacteria that expands the can.
You fill a 5-gallon bucket up with water.
Yeah, so those are both examples, and that's actually good. So let's talk about that for a second. I was actually thinking the same thing, and not like in that way, but like I know that like if you have like a can that's, you know, canned stuff lasts forever, but not forever. So like if you have a can that's really old, the stuff inside can actually expand the can out, right? So that's true. And with Brandon's example, both the radius and the height are going to change, correct?
Yeah.
With your example. But with Jacob's example, what's a little bit different about your example?
It's filling it up.
If we're filling it up with water, only one of those things changes now.
Yeah.
Do you guys see what I'm saying? So with this one, if we're filling this up with water, like here, okay, see how the radius is constant throughout the problem, but the height changes with your example. With Brandon's example, both of those things are changing in some kind of proportional way. So those are two different scenarios where one of them has a constant and one of them has two rates of change. Does that kind of make sense to you guys, what I'm saying? Okay, perfect. Okay, yeah. We're mostly going to focus on these types of problems in this class because they're easier, but that is something that could come up for sure. All right. So for the rest of the period, you can work together. It's due tonight, so make sure you get it done because, it's pretty easy. You're going to go through. You're going to take the derivative of all these. You're going to tell me what the formula is. You can Google it. I don't care. I will give you a list of formulas when we have a test on this. I won't tell you which one to use, but I'll give you a formula, okay? You're going to list the type formula, derivative, and then you're going to tell me a real-life example of where these things could be used in a variable rate. If you get stuck, do you see that list I have on eCampus with a little animatronics? You can totally use that. That may help you. And yeah, that's what we're doing today.